Welcome back to ECE 320A, the class before spring break. You wouldn't know it by all the full seats in the classroom, but we will continue. Thank you for being here. Some announcements. You don't have a homework due tonight or before spring break, but you do have some due right after spring break and an exam in 3 weeks, just so you can enjoy your spring break. I'm letting you know when your next exam is. That's on the 21st of March. And if you're interested in looking at how you might do some of these inverse Laplace transforms using your calculator, there are some videos available on the D2L website that you might want to check out. What I want to do today is remind us of these transform pairs, and these are useful when we actually end up with, when we're doing inverse Laplace transforms and we have polynomials in S sitting out in front of what I'm going to call and define to be a strictly proper transform expression. We'll talk about that in a minute, but now if you simply had to inverse Laplace transform a constant, that constant would be in the time domain. It would look like the weighting of that constant. Let's say the constant was 4 times this impulse in the time domain. Likewise, if you had an S sitting out there by itself, or an S squared, you would have the derivative of an impulse or the second derivative of an impulse. Hopefully that won't happen much in reality, but for educational purposes, we will deal with those types or these particular transform pairs. We'll then talk about the inverse Laplace transform of an improper f of s, and what do I mean by an improper? We'll define that, and we'll talk about the Laplace transform itself, or this complex frequency variable s. What does that really mean? What is that? Let's see if we can get an intuitive feel for S, and we'll talk about a low-pass filter example, and then we'll get into some inverse Laplace transforms. First, let's just set the stage for what we will need in a little bit, and that is this transform pair relationship between the impulse function, or impulse waveform, delta of t, and the Laplace transform of that and its derivatives. What are these pairs? From before we actually did perform the inverse Laplace transform of the impulse and putting that impulse waveform into the slot of our function that we're trying to Laplace transform, that now sifts out. Hopefully everybody went home and bought a sifter, or at least Googled it and found out what a sifter looks like. I'm thinking more about flour, not sifting rocks or something, but I'm more into food. So we now have a sifter, close enough, and it sifts out the integrand at the instant of time when that impulse is active. And that particular impulse is active right at t equals 0. That means it evaluates what's inside that integrand, or in the argument of the integral, at t equals 0. What's inside there is, and I missed a minus sign, but it's the same because it's 0, but it's e to the minus s times 0. That's when the waveform is evaluated. And e to the 0 is 1. That's the Laplace transform of an impulse, which means that if you needed to reverse that and find the inverse Laplace of 1, which is what this 1 is in the kitchen, if that's in the frequency domain, and the living room is the impulse, then if we say, well, what's this 1 in the kitchen look like in the living room? What's the inverse Laplace transform of a constant, with that constant being 1? In the time domain, that's this impulse function. So now on an exam, if everybody starts clapping, I'm going, yes, there's an impulse function somewhere on your exam. Yes. What letter is that? That's supposed to be a lowercase sort of delta. Does that look okay for that? So it's a Greek letter, and it's Greek to me. It's a delta, lowercase. Okay. I think that's the conventional symbol used for an impulse. Now if we just up that a notch by differentiating that impulse, what's the Laplace transform? Well, we know this Laplace transform operation associated with differentiation, that's multiplying by s, and it's also evaluating it at or subtracting the initial condition. But this impulse happens right at 0, and the initial condition would be to the left of that. So it's now s times the Laplace transform of this impulse, and we just found that to be 1. So now we have s times 1. We can do that math. That's just s. Meaning the pair, or this relationship, then says that if we wanted to inverse Laplace transform s, and that s could be scaled, then we would obtain in the time domain a scaled derivative of the impulse. And we could just keep going and going and going. We'll go one more step and say, what happens if we take the Laplace transform of the impulse differentiated twice with respect to time? We end up with s squared. Meaning, if we now needed to inverse Laplace transform from the frequency domain back into the time domain, we have this pair, or this relationship. We now know that the inverse Laplace transform of s squared will, in the time domain, actually be the second derivative of the impulse. That we now have. Yes? So now, what is the impulse function, or maybe we should just say impulse waveform? That's something that happens right at time t equals 0. And we're saying we would, if we looked at the derivative and Laplace transformed a derivative, we take s times the Laplace transform of the undifferentiated minus the time domain waveform's value evaluated at t equals 0 minus. If this impulse happens right at 0, not at 0 minus, not at 0 plus, in between those, then what the impulse equals at 0 minus is nothing. That's why we didn't worry about the initial condition when we used this derivative operational transform relationship. That answer your, so I think the question was, are we ignoring the initial condition on the impulse? The impulse, boom, it happens right at t equals 0. Not at t equals 0 minus, not at t equals 0 plus, in between those two values or locations in time. How wide is it? Infinitesimally small. How big is it? It's all the way up. What's the area underneath that, though? The area of an impulse. Do you remember? If you integrated the impulse, it has an area of 1. That's the definition of this impulse waveform. Is it's infinitesimally small in width, it's infinitely tall, but if you summed the area or found the area underneath it, it would be 1. That's what's weird when you start looking at infinitesimally small, infinitely tall. You can sort of make it be such that it appears to perform the way you want it, which is really having this integral of 1. I like to think of an impulse as if you now had a circuit and you excited it with an impulse, that now just energizes all of your energy storage elements in your circuit to some level, depending on how they are organized in your circuit. The impulse is gone after it, boom, kicks it, and then all of these energy storage devices just start moving in response to how the circuit is constructed. But you essentially have an initial condition response from an impulse hitting your circuit. Yes? So the question was, does that really exist in real life? No, by definition, but you can, I mean, if you were in the mechanical engineering domain or space, they have an impulse hammer. So you can have a waveform, and you could approximate this with something that has a very narrow time interval of support, and it has a really big peak, but you would want that area under that to be 1. So if you just looked at it very crudely, you would say, oh, let it have a height of 1, and then it's going to be, what, a width from -1/2 to 1/2. Now you shrink that width, you increase the height accordingly to give you the same area of 1 up until you can sort of say, okay, this is close enough of an approximation to this ideal waveform. And that might mean then that you have an amplitude of 10,000, and then your interval of support is narrowly defined. And you could make it triangular, you could make it like a rectangle in your approximation, but it's basically giving you the same kind of behavior. One fact before we, and this looks wordy, but you need to make sure you understand what this fact is saying. Before you actually perform any of these inverse Laplace transforms by this partial fraction expansion technique, you need to make sure that your numerator polynomial has an order or a degree less than the degree or order of your denominator polynomial. That's the fact. And if it doesn't, we have to make it be that way before we proceed with performing the partial fraction expansion. You can move straight ahead and do the partial fraction expansion on any transform, and you're not going to get the right answer if you don't obey this particular rule ahead of time. You'll get a number, you'll get numbers, but they won't be what you want them to be. Reading this then, it says before performing an inverse Laplace transform using partial fraction expansion, the degree of the numerator, and there I should have said the degree of the numerator polynomial, must be less than the degree of the denominator polynomial. And that's less, strictly less, not equal, less. And so another way of saying that, now on spring break, you can just start talking about things being strictly proper and improper. You'll now know what those mean relative to polynomials. You might not want to walk up to somebody and say, you look improper. That might not go over too well on spring break. But if they're an engineering type, they might actually understand what you're referring to. But here, the transform expression must be strictly proper before performing a partial fraction expansion. That's another way of stating that fact. And now let's define these terms, this one that I have in quotes, and some others. Strictly proper. That means the degree of the numerator is strictly less than the degree of the denominator. And there's an example. We have a first order numerator, we have a second order denominator. That transform expression is strictly proper. Middle. A proper is when the numerator's degree is equal to the denominator's degree. Here we have a quadratic in both the numerator and the denominator. Those could be both cubics. They could both be 10th order. That would still be a proper transform expression. The 2 or the power of the denominator doesn't matter. It's just the relationship between the denominator's order and the numerator's order. One more. We have strictly proper, we have proper, and then we have improper. An improper is when the numerator's degree exceeds the denominator's degree. Here we have a 4th order numerator, a 2nd order denominator. Boom, that's improper. We can't immediately perform partial fraction expansion on that particular transform. We have to do something to it before we continue. Is it clear, these definitions of transform expressions? You need to be clear on which one is which. When do I have an improper? And so the very first thing, if you see on an exam or a homework and it says inverse Laplace transform, this expression, your very first thing on your radar screen needs to say, let me check the orders of my numerator and denominator. If the numerator order is equal or greater, whoa, 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 I can't just keep going. I can't start immediately on my partial fraction expansion. If we can't just start, what do? We do long division, or you actually plug it into your calculator, and your calculator can do this long. If it can't, then you have to do the long division. Okay? So you divide these two polynomials. You divide your denominator polynomial into your numerator polynomial until the remainder, after so many steps, your remainder polynomial will have a degree or order strictly less than your denominator. Let's work through this example, and I'm going to scroll through this quickly, and then we'll go through another one on our own, or more slowly. Here's what we started with before. We have s to the 4th plus 3s squared plus 2 divided by s squared plus 3s plus 2. Or in factored form, we have a pole at -1 and a pole at -2. And you know, now you can probably see those poles under the circus tent. You can see the complex s-plane, and you can see an x at s equal to -1, another x at s equal to -2. What's the degree of the numerator? I've already told you, so hopefully you were still awake at that point. It's 4th order. The degree of the denominator is 2, and so this now says what about f of s? You walk into a restaurant and you say, this f of s is improper, isn't it? Has everyone, yeah, you walk into a restaurant. I've done the other and I've gotten into trouble. So we're walking into a restaurant. And what are you doing when you're walking? Have you seen the sign on 2nd? The digital sign, get your head out of your app. Yeah. Oh, yeah. So, yeah. Anyway, you're walking into the restaurant. Your head is not in your app, right? You can use this function in some of the TI calculators, your 89 or your Inspire, and you would actually obtain this piece. And now you can see, it may shuffle them around a little bit, but now you see the answer from the long division. You will get an s squared minus 3s plus 10, and now you have a numerator polynomial that has an order of 1 compared to your denominator polynomial that has an order of 2. And if you wanted to, you could then say, oh, I actually need to put this and find the partial fraction expansion. Well, if you have real roots in the denominator, this expand command works magic. It does the partial fraction expansion for you. Just saying. All right, so now let's go through that. We want to see, because some of you may not have that calculator, maybe I'll say show your work. That means you'll have to do the long division. We want to now figure out what goes in this blank for the coefficient of s squared, what goes in the coefficient for s, and what goes in the coefficient for the constant, or s to the 0. And then we've gone far enough in our division process, and we'll have a remainder that I'm calling capital N of s. Now, you won't write down that entire polynomial above the bar. You'll do it in steps. The first step is you go, oh, how many times does s squared go into s to the 4th? S squared. So then you multiply this by s squared. That's now what you take away from the original polynomial that was in the numerator, subtracting s to the 4th plus 3s cubed plus 2s squared from that original polynomial. And when you're doing this, you need to make sure that you're keeping track of which coefficients are or are not there. And in our original numerator, we were missing a cubic or a third power of s, and we were missing a linear power of s, or s to the 1. And I've intentionally spaced it out so that I remind myself, wait a minute, I'm comparing, hopefully, the same coefficients relative to powers of s. For the first one, I have this polynomial that I now need to subtract from the original numerator, and I subtract 3s cubed from nothing, and that gives me minus 3s cubed. Then I subtract 2s squared from 3s squared, and that leaves me with just an s squared. My next step is then to say, wait a minute, is this remainder of an order less than my numerator, my denominator's order? And it is not, so I have to keep dividing. The next step, I say, okay, what do I need to multiply s squared by in order to produce minus 3s cubed? Well, I need to hit it with minus 3s. I hit everything in this denominator with minus 3s, and I end up with minus 3s cubed minus 9s squared minus 6s. And I continue. I subtract that from the very first remainder that I had. Taking minus 3s cubed from minus 3s cubed gives me 0. That's good. Now I subtract minus 9s squared from s squared, effectively adding 9s squared. I'm sorry, have you had your hand up for a long time? Oh, I was just making sure we're all doing our exercises. Yes, question? Where did what? Where did the number 2 come from? S to the 4th plus 3s cubed plus 2s squared. Now what are you asking? The one in the blue underneath the division symbol? It didn't go anywhere. It's still stuck upstairs. It still is waiting to be compared with something, because I didn't have, when I multiplied my black polynomial above with the denominator, I hadn't yet generated a constant. And so when I compared my product expression with what I have in my original numerator. I didn't have a constant to look at yet. Is that what you were asking? You were asking about this. I was going to stand on that chair. Oh, that might not be a good thing. We need to get a ladder in here, don't we? Had a ladder last time, didn't we? We did have a ladder last time, yeah. Why am I doing this? That's the two you were referring to, correct? Okay. Catch me, please. How is this going to play on the video? Oh, all right. Let's not. I had a faculty member when I was about your level. He had a stool like that, and this was actually before I was at your level. It was earlier on. And we were studying potential, electrical potential. He was a little bit bigger than I am, about 6'4" or 5", maybe 300 pounds. He stood on a stool like that, and then he jumped off. The floor just went crazy. He said, "That's potential." Yeah, I learned potential. Okay. Where were we? We were still stuck on 2, weren't we? Now are we off of 2? And where were we? I think we were comparing this black line to the minus 3s cubed. Doing the comparison, we end up with 10s squared. We need to see, is this power less than the denominator's largest power? And it is not. They're equal, but it's not less. So we have to do one more step in the division process. We now need to create something that when multiplied by s squared gives us 10s squared. That one's easy. That's 10. We scale that denominator in every term by 10. Then, I was really just giving you guys time to catch up. I could have scrolled through this really quickly, but I'm allowing you now time to write. Now we end up with our remainder, and we can compare its power or order, which is first order, to our denominator's power, which is second order, and now we can stop this process of long division. Now we can say, oh, we have the terms we need plus the remainder that we're still going to have to divide by this denominator. And the remainder is then of degree 1, which is less than the degree of the denominator, which is 2. Meaning, we now have rewritten that original transform expression, which had an s to the 4th divided by an s squared, into some powers of s, in particular s squared, an s, and an s to the 0, polynomial plus a strictly proper transform expression. Is that a question? I thought it was maybe a wave. A question, yes.
It's not an impulse.
It's what?
It's not an impulse.
There's no impulse.
So my question is, can I keep going further with the long division so that I can...
So the question was, do I keep going with the long division? The answer is no. You go until you obtain a polynomial that's strictly less. Now it could be that the linear term vanished, then you would just end up with a constant, but that would be the first time that you came up with a polynomial that was strictly less than your denominator polynomial. Does that make sense? Meaning that minus 24s may not have even existed in that last step. Maybe it somehow vanished because of the combinations of the polynomials, and you just ended up with, let's say, 100 over s squared plus 3s plus 2. That's still where you would stop. You couldn't go back and say, oh, I've gone too far with my division. You keep going until the remainder polynomial is less than the denominator's polynomial, order of the denominator polynomial. We okay with that? This is why we talked about or just presented these first transform pairs that we introduced at the start of today's class. We said, what happens when we inverse Laplace transform an s squared? What happens when we inverse Laplace transform an s? Well, now it's scaled by a -3. What happens when we inverse Laplace transform 10? I don't know. Well, I told you what we do when we have an inverse Laplace transform of 1. 10 is just 10 times 1, so scale out the 10 if that makes you feel a little bit more comfortable. Now we have to inverse Laplace transform this strictly proper piece, and that involves a valid partial fraction expansion. I'm just going to say remember these pairs. That's how we now put those other terms that we divided out back into the time domain through the inverse Laplace with the appropriate scaling. And now we need to continue by inverse Laplace transforming that strictly proper form. Here's the partial fraction expansion. We simply have a factor or a term associated with one of those factors in the denominator. Oh, relative to these factors in the denominator, what can we say about the case that we are dealing with? Do you remember we stopped, I think, last time saying when we're inverse Laplace transforming, we may be in one of two scenarios or one of two cases. Do you remember talking about that? Distinct or repeated. In this case, we are in the distinct case. These particular values of s that cause the denominator to vanish are distinct. One is at -1, one is at -2. And that now says, oh, we have some term a over s plus 1. We have another term b over s plus 2. If we can find a and b, then we can take these back into the time domain. Because we know with these real roots, those are kind of easy. These are these decaying exponentials if the values of s are all in the left half plane. If they're in the right half plane, they're exponentially growing waveforms, and we can inverse Laplace transform those just as easy. Using the Heaviside approach, we can cover up the factor underneath a in our left-hand term and evaluate at the value of s where that polynomial underneath a vanishes, which is when s is equal to -1. Or we now evaluate -24s minus 18 over s plus 2 at the value of s equal to -1. Plugging in that value for s, we end up with a equaling 6. Similar process for finding b. We cover up the factor or the polynomial underneath b on the left-hand side, and now we have -24s minus 18 over s plus 1, and evaluate it where that factor underneath b would evaluate to 0, or the value of s is equal to -2. Plugging in those values for s, we end up with b being -30. And now we're ready to go. Now we can write down the full expression for f of t, the time domain version of that transform expression that we started with, which was in the frequency domain, capital F of s. We now have a impulse differentiated twice, -3 times the impulse differentiated once, plus 10 times the impulse. Now if you integrated 10 delta t, what would you get? If that's all you integrated was 10 delta t, what would the result of that integral? And you're integrating from minus infinity to plus infinity. You would just get 10. It's 10 times the scaled version of the integral of the impulse. And we said the integral of an impulse is 1. That's now our answer for that f of s. Let's go through another example just to make sure that we're clear on this. We want to now find what is f of t. This is a different capital F of s. So now we're saying, oh, we need f of t So if you're looking for partial credit, you might just write that down. You might get a half a point out of 100. 99.5 points you would miss, right? Oh, man. But anyway, that's better than a 0, isn't it? Yeah. So that's now where you get started, but can we continue? What's the first question you need to ask when you are confronted with a transform expression and you're asked to find its inverse? You need to walk into that restaurant, don't you? Yes, it needs to be proper, improper, or strictly proper? Strictly, doesn't it? So now we ask the question, is f of s, the capital F of s, is capital F of s strictly proper? What's the answer to that, or what's the condition that allows us to, what does strictly proper mean by definition? What's the relationship between the polynomial orders of the numerator and the denominator? We want the degree of the numerator to be less than the degree of the denominator for a f of s to be strictly proper. What is this? What category does this f of s fall into? It's actually proper, isn't it? It's not improper, but it is proper. So now this says no, it is not strictly proper. What do we do now? Now we need to do our long division. So we have our denominator, which was s squared plus 6s plus 8. I hope that's what it was. And we need to divide that into 5s squared. And note that I'm, again, putting some space in between my quadratic s and the constant term, because I know that I'm actually missing a linear power or an s to the first power. This is not difficult. We have 5 that would get s squared to equal 5s squared. We multiply 5, or multiply our denominator by 5. We have 5s squared plus 30s plus 40. And now we compare those, or take that polynomial away from the original numerator, and we now have minus 30s minus 38. Or we can now rewrite our capital F of s, because we can stop dividing. Our remainder now has an order strictly less than the order of our denominator. F of s is now 5 plus the remainder over our denominator. And this piece, if we were to call that f sub 1 of s, f sub 1 of s is strictly proper. And you could plug that original problem into the proper frac function on your calculator if you wanted to, and you should end up with this same result. And then you could plug this f sub 1 of s. Well, what's the first thing you want to do? You probably want to check where are my roots of that denominator. What does that look like? Can this be factored into two real poles or two real roots? Yes. 2, actually minus 2 and minus 4, right? So now this looks like s plus 2, s plus 4. We're in case 1. Those are distinct. Now we can perform the partial fraction expansion of f sub 1 of s. We now have minus 30s minus 18. Just making sure you weren't yet on spring break. Minus 38 over s plus 2, s plus 4. And that now we can say is a over s plus 2 plus b over s plus 4. And a, using the cover-up method, would be minus 30s minus 38 over s plus 4. Where do I evaluate that? At s equal to minus 2, the value of s that causes that polynomial sitting underneath a to vanish. And we now just plug in that value of s. We now have 60 minus 38. 60 minus 40 is 20. We need to take away a little bit less than 40. So now we have, what did I just say? 60 minus 38 is now just making sure 22. Okay, 22 divided by 2, or this is now 11. That's A. B is now minus 30, s minus 38. We're covering up the factor underneath s plus, or underneath b, so now we're left with s plus 2. What's the s value that we use? Minus 4. And now B becomes bless you, or minus 41. So that now capital F of S, we don't want to forget that we've already done a long division. It's now 5 plus 11 over S plus 2 plus a minus 41 over s plus 4. What do we have for the first term for our time domain expression for little f of t? Do we just have a 5? No, that actually comes in looking like an impulse, scaled by 5. Then what? What kind of mode do we have associated with s plus 2? Okay, we have 11 scaling an exponential, where the exponential's waveform is governed by minus 2t in the exponent, minus 41 e to the minus 4t, and that's true for t greater than or equal to 0. Now you can walk into the restaurants and do all these inverse Laplace transforms, right? Of course. So let's see if we can understand a little bit more about what's going on relative to going between the kitchen and the living room. You can kind of see these time domain waveforms, these decaying exponentials, these exponentially damped sines and cosines. What does this, when we get into the frequency domain, how can we maybe think about this frequency or this variable s? So what is the variable s? S now is a complex number, isn't it? Or we can evaluate it at any place in the complex S-plane, and that means it can be anywhere in this complex space, or be any complex number. Yes? So now, how do you find, the question was, what, you're getting ahead of me, you're already looking at the homework. Now what would happen if you had something like that? If these were now in case 2, if you had a repeated root or factor, then you would simply keep going with your partial fraction expansion. Now what you would need to do is you would actually end up with a problem when you tried to find b. You could find c by multiplying every term by s plus 4 quantity squared, and then you could solve for c by evaluating what's on the left-hand side at s equal to minus 4. You would end up with problems when you tried to find b, because then if you multiplied by s plus 4, which is underneath the b, then you would still have one s plus 4 downstairs on the left, and you would have one s plus 4 underneath c. And what happens when you evaluate those at s equal to minus 4? You get infinity equals infinity, which doesn't give you any useful information about b, does it? So you have to do a different strategy. You could solve for a and c. You might as well. You can get those with the cover-up method. But now to get b, you need to do a little bit more fancy manipulations. You could put everything over a common denominator and try to find a relationship, one of those equations that has a b in it, and solve for b. Or you could say, well, let me just plug in a convenient value of s. And a convenient value of s would be something other than minus 2 and minus 4. That gives you nothing, right? That gives you infinity equals infinity. Infinity and infinity. It's nothing, really, in terms of useful information. So you could plug in s equals 0, and now that gives you one equation. If you already know a and you already know c, you have one equation in the unknown b. Now you found a, b, and c. Now what do you do? Well, in this case, in the time domain, this looks just like what you did. b e to the minus 4t. This one now is c e to the minus 4t, but it has to be independent of what you just had, and it has an s plus 4 squared, so now this is c t e to the minus 4t. So you see powers of t in front of this mode e to the minus 4t. And now what you need to do when you go on your spring break and you're in the restaurant and you're drawing on napkins and looking at proper and improper, you go, what in the world does t e to the minus 4t look like? Is that t just keeps going, but e to the minus 4t dominates. So you kind of go up and then down. So as time goes big, as time gets really big, this ct e to the minus 4t is well behaved. It's going to die. It's going to go to 0. Right? So it's an okay term. It just grows a little bit when t dominates e to the minus 4t, but then it kind of bends over and we're okay. So you might plot that on your napkin. A t e to the minus 2t or a t e to the minus 10t, just to kind of see that shape. Does that answer your question? That's now what happens when you have case 2 or a repeated factor in your denominator or a repeated root. I'm going to erase that because if I don't, people start looking at these notes and they're going to go, why did he just get A and B? So now they'll have to listen to the radio. That's probably what they'll do. They'll say, well, the notes don't show it anywhere. Well, you should have come to class. So here, this wasn't even there, was it? Now are we okay? Oh, thank you. I was still in the restaurant drawing on my napkin. What? I was strictly proper, correct. I shouldn't have even said anything about, see, can't say anything around here without somebody interpreting it in, never mind. What is the variable s? Are there remaining questions on, before we start figuring out what s is or does? This is s, it is really a complex frequency variable that generalizes the phasor concept. And you had the phasor concept back in chapter 9, right? The phasor concept is when you're just continually shaking. You're doing sines and cosines. The S is a generalization of that. Before, you really kind of just had a frequency variable. Now we have a complex frequency variable. What is that? Well, now you can have exponentially damped shaking going on, or growing, exponential growth with some shaking going on. Let's try to get some understanding in that. So before you become all nervous and anxious, this S is actually designed to help us, not make us more anxious or nervous. It's actually designed to be of help. And the way that you can start thinking of this is now you can get very comfortable over spring break with this plane, the S-plane. Here is the imaginary component of S in the vertical direction and the real component of S in the horizontal. And if somebody said, oh, in this complex plane, and this is of infinite extent, it goes to infinity in the vertical direction, infinity in the negative vertical, right and left in the horizontal or in the real direction, all the way to infinity. If somebody said, oh, I'm interested in when S is equal to 0, then you would be thinking about what's happening when S is right there at the origin in the complex plane, when S is equal to 0. What about if we were at minus 2 plus J3? That was our S value. Then we would be at that location in the complex S plane. This is now when S is equal to minus 2 plus J3. In general, S is equal to minus sigma plus J omega. And it's a complex frequency, and its units are radians per second. I thought he was going to help us understand what this S is. It's a complex number. So let's now see what we can actually build with this piece of machinery, with this complex quantity, with this complex number. Look what we can build. With S. Suppose now that somebody puts that S in an exponent. They now say, oh, I now want to look at e to the st. And somebody says, yes, but he just said that S is complex. Let's now parameterize S into a real part, a minus sigma, and an imaginary part, a vertical part, which the vertical is said, oh, J, that says we're vertical, and we're going vertical in amount omega. Putting that expression in for S, we now have e to the minus sigma plus J omega times t. But now we can start utilizing some of our math skills and say, oh, this sum in the exponent, I can now separate that into two terms that are the product of those two terms. Because the product of these two terms, I can now just add their exponents. Or I can now distribute that t through both terms, and I now have an e to the minus sigma t, and I have an e to the j omega t. Where this piece, that should look very familiar. E to the minus 2t, e to the minus 4t. That's this exponential decay. What is this e to the j omega t? That's this rotating phasor, where if you wanted to think about it, what's the magnitude of e to the j omega t? If you now looked at the magnitude of e to the j omega t, you could say, oh, I don't know what its magnitude is, but I remember Euler. Euler allows me to rewrite that in rectangular form as a cosine and a sine. This is now cosine omega t plus j sine omega t. And if I look at the magnitude of that, I have cosine squared omega t plus sine squared omega t. I have cosine squared plus sine squared of the same argument, 1. So it has a magnitude of 1, and you could think of it for this, let's say omega is some value, 3, then as t moves from 0 to wherever, to infinity, we just have this thing spinning around with a magnitude of 1. You could think of it as this. It spins around at a rate omega, which then, where are we, depends on what t is. So if we plug in a t for a given omega, we're now at some angle in this plane. That this is, let's say, j, here's 1, and there's minus 1. This is now a spinning phasor. We have a decay weighting it as well. Well, if we wanted this to make maybe visual sense, we could say, well, let's just worry about the projection of this two-dimensional dot on our real axis. What does this look like in a real sense? As this spins around, just think of what's happening in real time or on the real line. This just keeps going between +1 and -1, +1 and -1. And how quick is it moving between those depends on omega. So this is now just going back and forth in a sinusoidal manner, where this is now the real of S and this is the imaginary of S. Let's now suppose that V of t is equal to V sub m e to the st. Suppose somebody now scales this e to the st. And let's just say, well, suppose s is equal to 0. What's this look like, this v of t? What does that look like when s, this complex frequency variable, is 0? Then we have v of t is equal to v sub m e to the 0t, which is v sub m. And what does that say about little v of t as a function of time? At time 1, what is little v of t? At time 5, what is it? At time 57, what is it? At time pi, what is it? It's always v sub m. It's a constant. So what does s represent when it's 0? dc, or a constant. It has a frequency of 0. This is now constant, or dc. Therefore, our signal with s equal to 0 corresponds to dc, or constant, signals. If s is equal to j omega, now we're actually in chapter 9. We've eliminated the real component of s, and we're saying, what happens if we're on the imaginary axis in the complex s-plane? That's what this is really saying. Then what do we have? Then v of t is v sub m e to the j omega t. And that's now a complex spinning phasor as a function of t. But we can make some sense of this by realizing or just rewriting e to the j omega t using Euler. So if we remember Euler, we have e to the jx is cosine of x plus j sine of x. Therefore, if we want a real signal to be extracted from that complex spinning phasor, we could say, well, let's just look at v of t as the real piece associated with v sub m e to the j omega t. Or we now have the real part of v sub m cosine omega t plus j v sub m sine omega t. And the real component of that complex number is just the real part of that, or v of t, is now v sub m cosine omega t, where this is now a sinusoidal signal of frequency omega when s is equal to j omega. So we've looked at when s is equal to 0. We've looked at when s is some point on the imaginary axis. Let's now go to the other possibility. Let's say what happens when s is equal to minus sigma plus j omega. Using the same thinking, if we want to isolate on the real component of this complex exponential, we would say, oh, the real part of v sub m e to the minus sigma plus j omega times t. Distributing the t and breaking that exponent into a product of terms, then v sub m is real, e to the minus sigma t is real, and we have v sub m e to the minus sigma t times the real component of that spinning complex phasor. And we know what that looks like. That's the cosine of omega t. Or v of t now becomes v sub m e to the minus sigma t cosine omega t. And what is that? That's now an exponentially damped sinusoid. And how did that arise? Well, that arose when s was minus sigma plus j omega. How did it shake? Its oscillating part was due to the imaginary component of s. How did it decay? Well, that was dependent on how far into the complex plane the real part was. That influences how quickly you exponentially decay and how far away you are from the real line in the vertical direction. What omega is tells you how fast you're shaking. Now we're ready for some analysis. Let's look at performing some circuit analysis using these S-domain ideas. And before we get too involved, let's start with a circuit that you might see on an interview. Suppose somebody now puts this on your napkin in front of you, and they're interviewing you, and they say, oh, here's a voltage source, V of t, here's a resistor, and here's a capacitor. And what is that circuit? How could you describe this in a phrase? What is this? Well, you'll know this when you come back from spring break, because you'll be analyzing this in the restaurant. What is it? It's actually a low-pass filter. So if somebody says, design me a low-pass filter, you could now put down an RC circuit and say, oh, here's a low-pass filter. This will now, if you put in some voltage signal, V of t, that has low frequencies and high frequencies in it, this circuit will actually produce at the output of that capacitor a filtered version of V of t, and it will prefer to pass, or you'll prefer to see across that capacitor the lower frequencies in that signal that you started with for V of t. This is now a low-pass filter. And now we want to figure that out with some analysis. So let's now say that this is the output of this filter or circuit. You could analyze this many different ways, but what might you prefer, or what might be your strategy? If this is now an RC circuit, what variable might you want to focus on in writing your equations? S. We'll get there, but now that's not one of the variables in this circuit just yet, is it? We're in the living room. We're in the time domain. So if we're in the time domain, and this is now on your coffee table, on a napkin, you've now drawn this low-pass filter, what variable might you want to be focusing on in writing the equations that govern the dynamic behavior of this circuit? Let's see. Okay, we're in the living room, but we've come from the kitchen, maybe, with a cup full of ice. Because we have a capacitor, we're worrying about Eli and ice, right? So now, what do we have? Do we have Eli and ice? Do we have ice? Do we have Eli? Do we have them all? We don't have an inductor right now, so let's focus on ice. If we're focusing on ice, what's the variable in that expression that we usually want to focus on? ICE. Let's see. ICE, and we have a relationship. We know I is equal to C dV dt. We usually focus on the variable that is the energy storage variable, or the derivative variable. So we need to focus on the voltage across that capacitor. So our strategy here is to write our equations in terms of the capacitor voltage. That's our strategy. But now I know that you guys are going to want to write everything in terms of a mesh current. That's your bread and butter. Now you are in the kitchen. But we're still in the time domain, right? What happens if we write a Kvl equation for this circuit? And if that's the case, maybe we want to think about what's happening with the voltage on that resistor. What's Kvl tell us? If I start down here and I write a Kvl equation from the lower left location, where do I go? Well, I go through V of t. I go minus V of t plus V sub r plus V sub c, and now I'm back where I started. There's my Kvl. Now I just need to focus on this strategy of writing everything in terms of the capacitor voltage. But Kvl now says I have minus V of t plus V sub r of t plus V sub c of t is equal to 0. This is a given. That somebody's going to have to hand us. That's the supplied voltage. We said we wanted to focus on writing everything in terms of V sub c and maybe its derivatives. Well, that's fixed. So now, or that's good to go. Now we just need to focus on the voltage dropped across that resistor. Is there some way of writing that or expressing that in terms of the capacitor's voltage? Well, if you're in the interview and you're still, your wheels are spinning, you're thinking, you're going, I need to buy myself some time. Let's see, V sub r of t, Ohm's law, you're thinking. You may not want to say that in your interview, but you say, oh, the voltage across that resistor is R times the current, but the current, I just have one current. That I sub R is the same as I sub C. So this is now R times I sub C. And then you pull out ice, don't you? And what does that say? That says that I sub C of t is equal to C dV sub C dt. So that now from KVL you have minus V of t plus the voltage dropped across that resistor, which is RC V sub C prime of t, plus V sub C of t is equal to 0. Was that an impulse? Well, you've you've tolerated me enough. I will stop here, but now you can take this into the kitchen, can't you? You can now Laplace transform this and see what happens for different kinds of applied voltages. And we may pick up at that point after break.